and welcome to this SWEP webinar on BPHE fundamentals and how to select and optimize braze plate heat exchanger. This is a 45-minute webinar plus questions where I will present this, or as we say in Sweden, mission impossible. My name is Adam Dahlqvist. I'm Business Development Manager here in North America, and there are my contact details. And I work for SWEP. And who is SWEP? SWEP is a brazed plate heat exchanger specialist. We were founded in 1983. Since 1994, we are part of the Dover Corporation, a US-based corporation, as noted on the New York Stock Exchange. Dover is a very big company. SWEP as a company is about 1,000 employees worldwide, serving about 16,000 customers. Those customers use or buy about 3.5 million braze plate heat exchangers from SWEP annually. And to be able to do that, SWEP has 5 factories, one in Landskrona, which is the headquarters, one in Kosice, Slovakia, sorry about that, Suzhou, China, Kuala Lumpur, Malaysia, and Tulsa, Oklahoma, for the US and South American markets. From Tulsa, we are serving about 80% of the heat exchanger for the Americas market is produced in Tulsa, and our typical lead time from there is 3 weeks. SWEP is approved by different third-party approvals like the ISO 14001 for environmental, 9001 for quality. We use Six Sigma in our quality work, and we have, for example, AHRI certified performance of our braze plates. These are some of our customers that we serve, and if you do not see your name there, do not despair. We will be happy to add your name to this list. One slide to explain the braze plate heat exchanger. If we start on the top left, we have the smallest heat exchanger that SWEP produced at the time being. It's a B3. It's the size of an iPhone 4, so it's a palm size, and it's inside the 6-inch port, or 150 millimeter, of the 649, which is the biggest one we have right now. And so the SWEP range is anything from palm size to a little bit more than 5 feet tall with 6-inch ports. What combines these two heat exchanger is that the operating pressure, the minimum is vacuum. The maximum pressure is, depending on model, 450 psi to 650 psi. SWEP also have high pressure or really high pressure units up to 2000 psi working pressure for transcritical CO2. Another thing we do with all our heat exchangers is 100% factory testing. So before shipping them to our customers, we have a test pressure that is 1.5 times the operating pressure. If the heat exchanger can take that, we then test it and see that it's not leaking to make sure that it adheres to the requirements that we have. Temperatures minimum is 321, which is about the temperature of liquid nitrogen. And the maximum is 437 Fahrenheit for the copper brazed. We will see that we have other types of brazing material, but this copper is by far the most common. And this is the maximum temperature for copper brazed. Certifications, as I mentioned before, it's we have the AHRI, which is a performance, UL, ULSC, SMSC or NPD, they are pressure vessel approvals. We have many more than these, but these are the most important ones for the Americas market. And the capacity, how big of a load can you have a braze plate handle? Depends on the size, of course, but what we will see is that the capacity of a SWEP braze heat exchanger they can take on more than what is traditionally known that a braze plate can do. If I'm going to show you how a braze plate is made, I'll show you 3 photos, and these are actually cutouts from an excellent SWEP movie on YouTube. So if you want to see the whole movie, go to SWEP's YouTube channel and search for what is a braze plate heat exchanger. But a braze plate is more or less pressing and stacking plates, as many plates it needs to meet the customer's requirements. Then we put them in a furnace to bake them, and when they are done and they are hermetically sealed, we then test them and make sure that they are all right, and then we send them out. If we look a little bit more in detail, what is inside there? So if we start with the plates we saw in the beginning, these are the heat transfer plates. They are with the pressed patterns in them. These are the ones that actually do the heat transfer job. So add as many channel plates as you want. Once you have as many plates you want, you put a start plate and end plate on back and end, front and end, and these are a little bit thicker to keep the pressure. You put the kind of connections you want, and in this case, you see that both the start plate has 4 holes and the back plate has 4 holes. This is normally not the case. You don't want the flow to go inside and out the backside before passing the heat exchanger. But this is to indicate that you can put the connections on the front side or the back side, or the hot side on the front side and the cold side on the back side, or whatever combination thereof. What you cannot see here is on this image here is the filler material. So let's look at that. So I already said that copper is the most common filler material, and then we have nickel and all stainless filler material. And the filler material is actually what you see here. This reddish shiny, that is the very, very thin copper foil that you can find between each and every stainless steel plate. There is this very, very thin copper foil for the copper brazed. What then happens, regardless of the filler material, is that when it goes into the furnace, the temperature goes up so high that the filler material becomes liquid, but the stainless steel does not. And this liquid metal will then creep up between the connection points of the stainless steel plates due to the capillary forces. And when the temperature is cooled down again, this liquid metal will become a metallic glue holding the stainless steel plates together. And that's it. The next one. So in that fashion, we do everything from the B3 with a 1/2-inch port, as you saw in the first image, to the 649 with a 6-inch port, which you also saw in the beginning, and then everything in between. These are not all the heat exchangers we do. We have more than almost 40 different models. So they wouldn't fit on an image like this, but these are the most common one in the HVAC and industrial applications. We will also have double wall units. I will go a little bit more deeper in detail, but this is a good overview of the different sizes we offer. And not to forget, AHRI certified. I will say it again. So AHRI is a third-party approval institution that what they do is to test our heat exchanger, compare it to the SSP that we'll also look at later, and see if they match. If the SSP, our selection software, and the measured performance of our heat exchanger match, then we become AHRI certified, and SWEP is that. And it's a kind of uncommon thing for brazed plate heat exchangers. So don't be afraid of asking if a brazed plate heat exchanger is HRI certified, because we are. Where can you find brazed plate heat exchangers? Let's start with the HVAC market. So we can find them in district energy, distributed heating or cooling. Typical then you have a central making heat or a central making cold, and then you go by different steps out to the end user. The closer to the end user you get, the smaller the heat exchanger, and the closer to the central you get, the larger the heat exchanger. The brazed plate is very common close to the user, but with increasing size, as you've seen that we have, the brazed plate is getting closer and closer also to the central, both for heating and cooling, because the brazed plate technology is efficient, compact, and cost effective. Another common application is tap water heating in different forms, heat pumps, HVAC, other types. We'll look into this later. Another common application is integration of different heating and cooling systems. So you have maybe district energy and a solar heating and a heat pump and something else that you want to combine into the end user, but you don't want to mix the systems. Then a heat exchanger, an efficient heat exchanger, is a good idea. Free cooling is another application we see growing quite a lot in Americas due to the mission critical or data cooling applications. Again, efficiency and compactness is driving forces there. Pressure breakers in tall buildings. When a building is very tall, the static pressure in the water tubes becomes too high and risks to burst the pipes. And if you have a heat exchanger, you divide that height and save the limit the pressure in the system. I know I'm going pretty fast here, but we will have a landing page. More common applications are in any type of refrigerant system, chillers, heat pumps, rooftop, dehumidifiers, anything where there is a refrigerant cycle and a compressor. And the functions that a brazed plate can do there is as an evaporator, condenser, which we'll actually look at in the SSP portion of this webinar, the superheater, economizer, subcooler, suction gas heat exchanger, oil cooler for the compressor, etc. In the more hardcore industry sector, we can see the brazed plates operating close to an engine, being a oil cooler or a jacket water cooler, and then making it to a combined heat and power machine. We can see it, for example, with compressors, inter and after cooler of the compressed air. And also there in compressors, there is oil coolers and different fluid coolers. Just examples, there are more things, but I cannot spend too much time of going through all the applications. But let's look on one of the more interesting ones, and that's the double wall. And why do you need a double wall, and what is a double wall? Let's start with that question. So a double wall is the cold side and the hot side that are close to each other, but not, there's something in between. There is a very thin open channel between them. That's the double wall. Why do you want to do this? This reduces the energy efficiency of a heat exchanger with about 25%, something like that. So you lose that efficiency. Why do you want to do it? Well, the only reason why you want to do it is because the extra safety that this gives. Because if there is a leak on either side of fluid 1 and fluid 2, and you don't want to mix them because fluid 1 is tap water that you're going to shower in, by using a double wall, you will be able to get this extra visible leak safety, so that before you get contamination, you will be able to identify the leak and exchange a heat exchanger. Where the applications where you can find where it makes sense to use a double wall is as a superheater or a condenser for a refrigerant system when you do tap water, or for industrial systems like an oil cooler or different type of energy recovery, where the end usage of the energy is to heat tap water. That was a double wall. I'll move on. So since this has gone pretty fast, I'll take a short summary. So brazed plates are stainless steel plates bonded by a filler material that is typically copper, or all stainless. SWEP product range is pretty big, and it extends beyond what traditional limits say. When I speak with engineers, they say, well, a brazed plate, they are up to 1, maximum 2 inches of port. We have 6-inch port. So the capacity that SWEP can solve are well beyond what is commonly known on the market. All our heat exchanger are pressure and leak tested before shipment. Double walls provide extra safety for tap water. and where you can find them, what kind of fluids. So heating and cooling of water, glycols, brines, and pressurized gases. Why do I say pressurized? Well, for an air dryer or a compressor where the air has been pressurized, it can pass through the heat exchanger without a problem. If you take ambient pressure air, for example, the braze plate is not good enough. Then you need an air coil. But for pressurized gases, we can do it. Any type of oil, hydraulics, engines, and transmission oils, and then refrigerants. And the two of the most common ones right now is 14A and 134A. The new ones come in. It could be R32 or propane, and braze plates are good with all of them. Also, ammonia is possible, but since ammonia is aggressive to copper, all stainless heat exchangers are needed. I will move on. So let's go a little bit deeper inside how heat transfer works in the braze plate. So every two plates, these two plates create one channel. So for each two plate, you get another heat transfer channel, and by adding more and more plates, you get the hot side, the cold side, the hot side, the cold side, the hot side, the cold side, etc. So the hot and cold side, when it goes in, they will be have a lot of surface contact with each other all along these alternating channels, and that is what makes the heat transfer so efficient, together with the turbulence inside. We will look at that. So the information we need for you, dear customer, is how much energy do we need to transfer? What are the temperatures and flows? What kind of fluid or media are you planning to use? And what is the maximum pressure drop that you can allow when the fluid goes in, through, and out, right? And with this in data that you give us, we can choose the BPHE platform, everything from the B3, the palm size, to the 4-inch monster, 4-feet monster. So that sets the height and width of the heat exchanger, and then we start to add plates from the minimum of 4 plates up to the maximum of 400 something, and so then we have the size and the heat transfer area. And to know which platform to use and how many plates, we have to balance the thermal length and the pressure drop, which we will look into now. So what is the thermal length? We can categorize them into easy, difficult, and tricky. So we start with easy one. What's an easy thermal length? Well, it is if the hot side and the cold side has a very big temperature difference. And we're measuring temperature difference in logarithmic mean temperature difference. That is, if this difference is large, we call it as a thermally short case. So not so much heat transfer muscles are needed. So typically a short and wide heat exchanger that doesn't give so much pressure drop is the typical choice here. When the temperatures get closer and closer, the LMTD gets smaller. This is a thermally long case, and to be able to squeeze out all this energy that is required, a tall and narrow heat exchanger is required, but this will cost more pressure drop. So you will have to be willing to pay more pressure drop for this kind of case than that one. And then comes the tricky one. And the tricky one is if one side is, so to say, sloppy, not so much thermal length, and the other one is thermally long. So what we'll have there is an unbalanced thermal length. So to do that, we have to oversize the heat exchanger to meet, to be able to meet this requirement. Well, the other side will be very much overdimensioned, overshooting the target, or we can use an asymmetric heat exchanger. And the obvious question is, what is that? And let me come to that. So the difference, the easy and the hard and the tricky heat transfer cases, the tools that SWEP have developed in our models to meet requirements like that are included in H and L type of plates, high thermal length and low thermal length plates. So in the high thermal length plates, the flow has to follow a longer path inside the heat exchanger, making more pressure drop, but also more heat transfer. In a low thermal length, the path is quicker, less pressure drop, but also less thermal length. Another parameter that SWEP have in our different models are the pressing depth of the plate. A big pressing depth gives a low pressure drop and a short thermal length. And a little pressing depth has higher pressure drop and longer thermal length. You have to keep your tongue in your mouth in the right way to say it. But it becomes kind of logic when you see it. This is more squishy, so it will be smaller, higher pressure drop, but it will also be closer together. The fluids are closer together, so it will be more energy, more energy efficient, so to say. And then comes down to the symmetric plates. So what is that? And let's start with a symmetric one. So in a symmetric one, we are using all these data up here to combine a symmetric heat exchanger, but they do look the same. So the cold side and the hot side, they look exactly the same. There might be a H or L type of plates, but they look the same. However, an asymmetric heat exchanger, that is, one side is the thermally long one because it's narrow, and the other side is thermally shorter because it's a wide side. And then you can combine the have a thermally long or a high pressure drop side and a low pressure drop side. When is it needed? Well, if we have a high flow versus low flow side, if we have a gas versus liquid, oil versus water, or similar. And in our SSP part, we will give an example to this. One more thing about LMTD, and this is kind of important, that so the LMTD, this is the definition, and we saw it before. The closer the hot and cold are together, the more energy efficient the system is, the more energy you squeeze out, right? Which is good. However, the smaller the LMTD, the closer they are, the more heat transfer you need, but it's not linear. Actually, the amount of heat surface area required with a diminishing LMTD increases with the power of the LMTD. And the first law of thermodynamics, which is what you see here, meaning that if you want them to meet, if you want them to kiss each other, you will have to use an internal heat exchanger. And the first law of thermodynamics will not budge. I have met a lot of more intelligent engineers than I who have forgotten about this because they have a very good simulation and they want an internal heat exchanger where the temperatures cross, and I have to persuade them that I cannot do it. But just going from 6 to 4 to 2 will increase the required heat transfer area quite a lot, which we'll also look into in the SSP section. So let's look into SSP. What is SSP? SSP is actually our software package. It started on an HP calculator back in the mid 80s. It then developed in DOS and then Windows version. It has then developed in different levels, and now we're at the generation 8. How is SSP evolved? Well, I would like to start with the application management. That is a function in SWEP headquarters in Landskrona that verifies that SSP is doing what it's supposed to do. It prioritizes requests and issues, and backend technical support to make sure that everything works. They are in the center of the web. An important group is the heat transfer research group of SWEP. They do a lot of simulations of heat transfer. They do a lot of lab testing of the brace plates to see how they match the simulations. And based on the test, they then do correction factors and implement them into the the SSP calculation core so that the SSP calculations meet the lab tests. Then we have our in-house software engineers that do the guided user interface, integration with other SWEP systems, so that the SSP is not only a calculation tool, but it becomes completely selection and dimensioning tools with a lot of extra information needed for you and for me. And then, of course, you and me, what do? Well, we select brace plates to our heart's content, and we can send feedback to AM when we see something strange, if we see something strange. But I would, of course, recommend that if you are doing calculations with SSP and you see something strange, please reach out to me or anyone else in the SWEP team here in Americas, and we will see if we can sort it out with you. And this is how it looks like when you start. So it's on the up here is a calculation menu. We have different types of calculations methods. SSP is free to download and free to use. When you do so, you will not see all of this because you will have the demonstration mode or demo mode. When you register with name, email, telephone number, etc., so that we, so to say, we can have, so we know who you are. You get access to all, the calculation methods that are necessary for your business. We have contact data down here. In the mid, we have information of our product portfolio. We can directly start to find information about the products we have. Latest news, and up here there are case stories and examples of installations of SWEP brace plate heat exchangers. Up here you can actually send directly inputs to application management, and here are the release notes if you want to see what's happened with the latest version of SSP. So all good. Now let's go to SSP, but how do I know what data is needed to make a good SSP selection? And I'm glad you asked, because we have developed a small, simple tool in Excel, template for SWEP template for in data to SSP. We have a single phase and an evaporator condenser tool here. So this is only to guide you to what kind of information is necessary. Like we have a 100,000 BTUs, we have 50 degrees in and 60 degrees out, whatever, right? And then if you start to do, and we have 5 GPM, this is actually too much data. If we have both the BTUs, temperatures, and flows, it's over. The system is over-spec'd, and that is why we have this. Don't give us only 2 of the 3 in this one here. The same for evaporator condenser. Here, of course, we are looking at the liquid temperature before the expansion valve in an evaporator, or the evaporation temperature. For a condenser, we would like to have the gas temperature or the discharge temperature from the compressor, and then the condensing temperature, etc. I will let you look into this more in detail, and if you have any questions, please reach out to us through our contact data, which is on every page. One more thing though, in the last pages here, you have a little bit of a tool where you can see, where you can change the temperatures, and so you can be helped and find what is the LMTD, what is the minimum temperature difference, or what we call the pinch, and you can also see what I was looking before, the thermal length from each side, right? Because if these are very different, so if I go 195, so now I have the blue side, the cold side is very thermally long, and the hot side is much lower, of 0.67. That means that this is, since these are very different, these data call for an asymmetric approach to the this is a tricky one, right? And if they are instead very much the same, then this is a perfectly symmetric case. But I will. This is if you want this tool, please reach out to SWEP, and we will send it to you. It's a free to use in-house. So that was how to find out the data we need, and now let's look into SSP. And I will say like this. So what we will look at here, we'll look at 4 cases: water to water, where we'll be changing the logarithmic mean temperature difference and see what happens. An oil to water, comparing symmetric and asymmetric solutions. An evaporator at different distribution devices, and a condenser, balancing the pressure drop on the water side and the condensing temperature. So let's start with the water to water changing LMTD. And I have actually prepared a little bit in before here to make it smoother. So with a 1 million BTUs, I've entered 1 million here. Temperature is 180 to 150 on the hot side, you see there. 130 to 160, that's there. And then maximum pressure drop 3 psi on both sides. Maximum pressure drop 3 psi. What I also did was actually to go to the filter, and I chose the factory of Americas because I wanted to be made close to me to have this 3-week lead time. What I got then is a B35 M50 plates, and now SSP is calculating, so I have to wait anyway. And here we are. Yes. So since I can see all the technical data here, including the LMTD is 20, which I know. The thermal length are calculated, the temperatures, or all the selection data can be, the thermal data can be found on this first page. The dimensional data, you can see directly here what is the height and width of the heat exchanger. And this one here, the A, small written, but A is the height. It's about 16 inches. The B is the width, and that is about 10 inches. So it's kind of, a short and fat heat exchanger, so to say. Going back here. So this is what we expected, because it's a thermally short, and then the pressure drop will be the limiting factor. So that's what we got. Perfect. Let's look on the second one. So it's exactly the same in data, except for that the temperatures has come a little bit closer. So 150 became 140, 160 became 170. And what do we see here? We see that the LMT has gone down from 20 to 10. Yep, we increased, we got 10 Fahrenheit closer. And this heat exchanger is now, B is the same width, so it's still about 10 inches wide, but the tallness has now gone up to 21 inches, from 16 to 21. So it's a thermally longer, needs a taller heat exchanger and more heat surface area, as we see as well. And the last one, let's see here, move it over there. The last one is going even closer, 180 to 135 and 175. So we're going up to only another 5 Fahrenheit closer. So now we're down to LMTD 5, and now we have the same heat exchanger, 120T, as we used before. You can see the 120T, 82 plates, and 120T, 193 plates. We have more than double number of plates and went 2-pass. So what we can see here is that the heat transfer surface needed has gone up with the first step 132% and the second step 137%. So it starts to increase rapidly. And I assure you, if you start to go down to 432 LMTD, it will just raise up to the highest numbers. But this is quite interesting. What is this 2-pass? What is that? Let's look. So a 2-pass is a variant. The most common one is a 1-pass. A 1-pass is that the hot flow, the red, it goes in, goes up, and goes out. It's like a U form. It goes, like a in and out. 1 pass through the heat transfer channel. A 2-pass Then the heat, if we follow the hot flow, it goes in, it goes up through the heat transfer plates, but instead of leaving the heat exchanger, it continues over to the second part of the heat exchanger where it goes down again. So you actually have, it's like having a heat exchanger with a double height and of course also much higher pressure drop. So with increased thermal length, where a single pass is not enough, you can have 2 pass or even 3 pass or more to have the heat exchanger become like a 2 times, 3 times, 4 times taller heat exchanger. And it all comes out with the smaller the LMTD, the longer heat exchanger you need. And that is what we it's up for our discussion between SWEP and you, dear customer. What is the sweet spot between energy efficiency and heat transfer surface that we throw on the problem? Good. Let's look into the oil, an oil cooler. So I will change my calculation window here. So in this case here we have an ISO VG68, and I'll just show you how to make the how to find fluids. So I know that I have an ISO VG oil, which is a standard, and then we can see all the ISO VG oils here. We could also have found them in by going to industrial fluids, oils, go down, hydraulic oils, ISO VG oils, tellus, and you can find them there. But if you work in the oil business, you probably know what kind of oil you're looking for, so you don't have to. You can do the immediate search. So that was the oil side. In this case, we do not have a capacity, but we have an inlet temperature, we have a target outlet temperature, and we have an oil flow on the oil side, and we have a pretty hefty maximum pressure drop of 15 psi. On the other side, we have water in at 90. We don't know what the temperature out will be, but we do know that we have half the flow of the oil. And on the water side, we have a maximum pressure drop of 3 psi. So when we do the calculation, we get 2 heat exchangers. One is asymmetric and one is symmetric. The ADAS is asymmetric and has a 19 square feet surface area, and the B8538 is symmetric. And as I said before, since it has to meet this, the water and oil have different requirements, it's more, you need more plates to meet both of the conditions. But while the asymmetric can shortcut this. This is all well and good, but let's see if we further accentuate this difference. We do exactly the same calculations, exactly the same temperatures, 150, 120, 16, 15, etc., but with an even heavier oil. So we take an ISO VG 220, and now we can see that the difference is much stronger. We have the same heat exchangers comes out, but even with the asymmetric heat exchanger, we have to double the number of plates with this much heavier oil. But with the symmetric heat exchanger, we more than double, and we go up to 100 plates. So it shows with the more asymmetric type of fluid, asymmetry makes more sense. It's not asymmetry is not a one size fit all, but it will help you if the 2 fluids or the 2 capacities are asymmetric. Jolly good. Let's do the evaporator. And now I will close this down, and I will go to an evaporator and do it like this from scratch. So what we have here, we have, and I will, since I want a V80, I want a P80, and I want an F80. They are the same heat exchanger. The only difference are 3 different distribution systems. I have 10 ton, 120. I can change this down to US ton, 10 tons. You have the temperature of the hot side of the expansion valve is 100, meaning the temperature out from the condenser, including subcooling and everything. We have a target evaporation temperature of 36 and a super rate of 10. And the pressure drop on that side is actually not used normally. On the water side, we have 54, 44. And the maximum pressure drop of 5, a little bit higher. Okay, let's run that. I did something wrong. There it is, 40. Sorry about that, 44. Ta-da, yes. So we got the same heat exchanger, right? 42 plates, V80 42, P80 42, F80 42. They all look the same. What we do see is that we can see the pressure drop in the distribution system. For the V80, it's from 0.9 to 1.3, average 1.1. The P80 is the pressure drop in the distribution device is 2.1 to 3.2, average 2.6. And the F80 42 has even higher, average 8.4. So which one of these, they are, same number of plates, which one should we choose? Well, we'll wait with that until we see what's the difference with the other ones. So we do the second one, which is exactly the same data. The only difference is that now the target evaporation temperature is 39. We run again. And what do we get? Well, we get that the V80 is out of question. It's not even selected anymore. The F80 is still with the same number of plates. I'll see if I can show that to you. The F80 is with the same number of plates as before, but now since the evaporation temperature is higher pressure, the distribution system pressure has gone down from 8.4 to 7.8. And the P80 is still in the game, but had to increase the plates a little bit. Not so much, but a little bit. And here we have now a pressure drop of 1.7. So there seems to be something with the distribution system, doesn't it? And then let's take the last one. So the last one is we go up another Fahrenheit from 39 to 40. That's not so much, right? But look what happens. Now, you can already see it there, right? I already put it down, but I want to show you live. So the F80 comes with 54 plates and an average of 4.5, and P80 starts to run away with plates. Now it's 66 plates, and the distribution system is down to 0.9. So there seems like the distribution system has a value here. What is it that we're looking at? What is the good distribution system? Well, a distribution system, what does it do? It is typically a ring, even though we have other systems, but let's simplify it. So it's a ring in the inlet of the refrigerant when it comes in the bottom of the heat exchanger, where a well-defined inner diameter and an orifice diameter. What it does is, depending on the refrigerant and depending on the mass flow, or the conditions of the case, this distribution system has to be able to solve the problem of the gas wanted to take a shortcut. If the distribution system is not there or not well designed, the refrigerant gas, when it comes in, wants to take a shortcut and finds the fastest way through the heat exchanger, as you can see here. So the dark blue is the refrigerant liquid that has to evaporate and leave a lot of latent energy inside the heat exchanger. And all this area here is just the gas running away and taking the shortcut out. And in this case, only 50% of the heat exchanger that you paid for is actually doing what you want it to do. And 50% is just a gas heater, not efficient. A good functioning distribution system makes sure that the gas is not allowed to take the shortcut, but is equally distributed together with the liquid, so that as much as possible, or 70% of the heat exchanger that you paid for is really evaporating. And how much pressure drop is too much? And that actually, we don't know. You have to decide. And that is why we have to look at this before we select which heat exchanger you want in the case. This is the log pH diagram. Again, I will not go this too much, but up here is the condensing. This is the condensing pressure. It's the same pressure all the time here. And down here is the evaporating pressure. So the same pressure along this horizontal line. Between the condensing pressure and the evaporating pressure, there is an expansion valve. So all this is what the expansion valve does. It goes from the high pressure to the low pressure. What we do with our distribution system is to steal a part of the pressure drop over the expansion valve and put it in our distribution system to hold back the gas. We have noted that this one, if we steal more than 30% of this one here, and you're using a thermal expansion valve, the expansion valve can start to lose its grip, can start to lose its control. If you're using electronic expansion valve, you can actually, we can use much, SWEP can steal much more of this pressure difference, but it depends on what kind of expansion valve you have. So that's why we normally say maximum 30%. So if we go back to the selection here, I would say which is the best evaporator here, and you have to decide. Can you accept only a little bit with 1 bar? Then go for the V80. Can you accept the 2.6 bar? I would recommend the P80, because you will have a better evaporator in this case. And I don't think you can accept the 8.4 bar here, because that would be 8.4 bar would be more than 30% than the total pressure difference in a 14A system typically. And then the same question goes from the average and the high end evaporator. For this one here, it's the P80 is probably the Goldilocks choice here, and for the really high efficiency, you have to go with the F80, because that's since SWEP is a recommendation of more than 1 bar in the distribution system to make sure that it really works during all the conditions. I would say it's the F81 for the highest one. So your choice here, I would go for maybe the P80 was probably my Goldilocks choice here, and here I'm forced to go with the F80. So that's the distribution system for you. Any questions, please reach out to SWEP. The last one, the condenser. And here we will look at, I will kill this off, 1, 2, 3, and go to a condenser. And let's enter the data here. 500,000 BTUs. That's a 500,000. Inlet temperature is 158. Okay, that's the discharge temperature. Target condensing temperature is 105. Subcooling 10. Water side 86, 95. Okay, I took the standard numbers. And the maximum pressure drop is 5. Let's do that. See what happens. B250AS, so an asymmetric heat exchanger. It makes sense. It's a condenser, it's a refrigerant and water with 90 plates. Yep. So, and we see what I want to point out this time is the oversurfacing. So this heat exchanger, it's SWEP, SSP says it's oversurfaced. There is more surface than needed to meet the thermal conditions, but SSP added plates to be able to reach the 5 psi limit here. Okay, so we do the calculation of the second case. What do we change there? Okay, so we went down 2 Fahrenheit in the condensing temperature, but everything else is the same. Let's see what happens. Well, it's already here, right? But I want to make you see it. So it's exactly the same heat exchanger. The pressure drop is the same. Over surface is still there, but it went down, right? So here we have 34% over surface because it's related to the 105. Now it's 15% because it's related to 103, but it's still over, it's too much, you know, it's still a little bit over dimension. It's not a problem, either one of these, but it means that your limit of the pressure drop and the target performance are not, we cannot meet it, so we have to over dimension the heat exchanger a little bit. So if we take the last one, so now we're going to an even lower, from 103, right? From 103 to 100, so we go even down in the condensing temperature. And now we get a slightly bigger heat exchanger, up from 90 plates up to 114 plates. I'll just let you, here it comes. So now the pressure drop, before it was 5, right? Now it's 3. So we have been able to, now it's not pressure drop restricted anymore. The over surface is down, meaning that now the heat surface that we have added to this heat exchanger will meet, you know, will meet the 100 degrees target condensing temperature. So these are the you know, this is how pressure drop and thermal length or performance is interacting. So if we go back to the calculator number 1, let's say that you are you're in the case that you just want a basic condenser, 105 Fahrenheit condenser, you don't care so much. But what you could do to reduce the number of plates is you can accept a higher pressure drop. Let's go up 1 psi, see what happens, from 90 to, come on, okay, from 90 to 80, 10 plates. We changed that 10 plates. That was pretty good. If we go back to 5 and then change another parameter, we can say that the, I'll extend it a little bit. Since we have the temperatures we entered was 86 to 95, right? And with the BTUs and everything, the water flow becomes calculated by SSP to almost 112 GPM. Let's say that we can, well, we can reduce the flow a little bit. We can accept a higher water out temperature. Instead of 95, let's go 97. But keep the 5 psi. You don't want to accept a higher pressure, but let's go up to Fahrenheit. What happens then? And voila, we go down 18 plates, right? And now this is almost a perfectly balanced heat exchanger. So we reach the 5 psi, plus a little bit bonus with complements of SWEP, and an over surface of 0. So in this case, having 91 GPM instead of 112, allowing for a little bit hotter water outlet temperature, you can save 18 plates if you want to. Or you can just go back to the heat exchanger you had before and click auto performance. So now we're back to exactly what we had before, 105, 10, 86, 95, but with auto performance. What kind of condensing temperature will I actually need if I do this selection? And you will get the B250 AS with 90 plates, but the condensing temperature when SSP is, so to say, iterating out what kind of performance will you get from this heat exchanger, you will get a condensing temperature of 101.55. So if you can, or from this starting point, you can, by changing some parameters, you can get a cheaper heat exchanger, or you can get a higher performing heat exchanger. It's up to you. And these tricks and others, we will be more than happy to go through in detail with you for your company, for your project. So please reach out to us and play with SSP, talk to us, and we will help you to get the most out of it. So that's it. that was about 1 hour of very condensed information. Please do not hesitate to reach out to Summer, to Adam, to anyone in the SWEP sphere. We will be happy to help you, and good luck with SSP. Thank you, everybody.